Okay, so picking up where we left off, kind of. So last time I think I may have mentioned, but we've actually, as of Wednesday, already finished covering all of the new ideas in Chapter 7. And so today, we're still going to be in Chapter 7, but I'm not going to be so much introducing new ideas as kind of organizing existing ideas. So y'all have seen this diagram before. Again, reminder, this is available on the class website in the class materials section. And, question.
Sorry, is this lecture recorded?
Yeah, it's, I believe it is. Let me check the... Yep, it's going. Yeah, we're good. Yeah. What I want to do is walk through this some more, what this diagram, how this diagram works and what it can do for you. So the big idea, remember, is there are some very sophisticated ideas that we are not going to talk about in this class, that if you kind of boil off a lot of the formality, this is what's left over. It's just an organizational strategy. I think it's a nice way to think about it. Don't think of this diagram as proving anything. Okay? But if you just think of the ideas as they are laid out in this diagram, weirdly and mysteriously, good things will just kind of automatically happen a lot. Right? So let me walk through some of the nice things we've talked about. So let's take the fundamental theorem of line integrals. Fundamental theorem of line integrals says that if you take the gradient of a function and if you look at the boundary points for a curve, then this kind of an evaluation of your original function on those boundary points, this kind of an evaluation of your gradient on your original curve, you get the same thing either way. Okay, so we've talked about that one before, and just as a shorthand, just because it's kind of flows easier, I like to write this about like that. It's just a little bit easier to mark up on the diagram. So as we've already discussed, this pattern holds even for theorems that are geometrically entirely different and disconnected from this theorem itself. So we saw that with Green's theorem, and now that we've got Gauss's divergence theorem, we can make that observation here. Right? Exact same pattern. Gauss's divergence theorem says that if you take a vector field and look at its divergence, if you take a solid three-dimensional region and look at its boundary surface, right? And if you look at the flux on the left and the triple integral on the right, you get the same thing either way. So exact same pattern. Ditto Stokes's curl theorem, right? Exact same pattern. So what I like to call an eyebrow raiser, right? This should be strongly suggestive to you that there is an underlying good reason that we'd want to lay things out in this way. All right. Now another thing we've talked about, and I haven't pointed to this part of the diagram yet, and this is this is not proving anything, right? But just kind of organize ideas. These two lines here are making a reference to how there's a connection between curl being 0 and a vector field being a gradient. The little notational choice that I made here is that solid lines represent a hypothesis, and then the dotted line represents the conclusion. So, for example, this says if you have a vector field that is a gradient of some function, so if that is the case, then the conclusion is that the curl of that vector field is 0. Okay, and then of course this other statement down here says sort of the backwards of that. If curl is 0, then that vector field must be the gradient of some function. All right, so again, old theorems, not new ideas, but this is just how I like to write it on the page. Okay, now here's another thing that we've talked about. We've talked about special vector fields. So in particular, there are some special vector fields here. I have to emphasize, just to avoid possible confusions, these are special vector fields. What I'm about to write down are not true of all vector fields. of course. These are just certain special vector fields. These special vector fields are gradients. Gradients also have the feature that curl will always give you 0. Again, those were some of the lifetime theorems that we just talked about, otherwise known as local tests, as we presented them in chapters 6 and 7. And then there's this other property called path independence that, look, if you have two different curves, but if they have the same starting and ending points, special vector fields will have this feature that you'll get the same value of the line integral on those two different curves because they have the same boundary. So again, 3 different properties. Now again, we've written this down before. What we have not really quite been able to do is to see how this pattern actually translates. And so here we go. This little pattern of 3 properties, 3 different properties of the exact same vector fields, ignoring regularity issues. I got to throw that in there. There's some weird stuff that happens if you have discontinuities or whatever. So among nice vector fields, all the vector fields that we're talking about have all 3 of these properties. If you slide this over, it still works. And again, it's just amazing that the pattern is this strong. But there are special vector fields, namely curls. Curls will always have the feature that divergence will be 0. And further, will have the feature that if you have any two surfaces with the same boundary curve, those special vector fields will give you the same flux. Right? So, a completely different trio of properties, but they follow the same pattern. Right? So, because of this diagram, because of how we've laid this diagram out, because we've composed these operators in that order, anything that you understand about path independence, you can translate to an analogous result about surface independence. And I think this is super useful, right? I mean, I'll reveal that, when I'm thinking about, computing a flux or computing a line or whatever it is I might have to compute, I have this, backwards across my eyelids. This is what I am seeing when I'm thinking about how to do those computations. I think about which column am I in, and what am I doing, and therefore which properties are available, and which theorems may apply, etc. Okay, all right, so I wanted to note all of that. Now what we're going to do is we're going to go on to these examples that we have. We just got through doing all of that. There are 6 examples here that finish up the Chapter 7 notes. And I'm going to talk about how to use the diagram to diagnose what method you should use to answer one of these kinds of questions, right? So, here's a bunch of specifics, and the punchline is I want to compute a line integral. Should I use Green's theorem? Should I use path independence? Should I use Stokes' theorem? What kind of a problem is this? Right? So how do you tell? And roughly speaking, the answer is know your diagram, identify where you are in the diagram, do what the diagram tells you to do, right? And infer accordingly. And the diagram, again, if you follow the pattern, the diagram will basically tell you what your options are. Okay. All right. So let's walk through that, starting with this example right here. Now, step 1. Where are we? Which diagram were we even talking about? Where in said diagram is this problem taking place? Okay. First observation. Our vector field. You see right there, 3 coordinates. This is a 3-dimensional vector field. Look at the parametric curve we're given. 3 coordinates. Right? Again, clearly this problem is happening in 3 dimensions. So let's go back over here to our diagram. Notice this diagram says R3. All right, so this diagram applies if your question's in R3, which ours is. If the question's in R2, then you would look at this diagram. Okay. All right, but we're not going to waste our time on that diagram because we're not in R2. We are in R3. Okay, what else? Well, the question is asking me to compute a line integral. That's more evidence of where I am and what I'm. This helps me with my context. Line integral, after all, right there. Okay, so that's my context. This is where I am. I am looking for a line integral in R3. So there I am. Now you can see right away there's a couple of places that line integrals show up. Obviously, they're right there in that position where line integrals are. And so I know that my two theorem options, my big gun possibilities, are these two right here. Okay, so we already know what the candidate theorems are that I might be able to use. Is that cool? Everybody on board? Also, very importantly, I have now further established what I definitely will not be needing and will not have any potential to make use of, and that is Gauss's divergence theorem. Look, it's way over here. Gauss's divergence theorem doesn't have anything to do with line integrals. Right? So very important also. Now this is from a strategic standpoint, right? So y'all are all going to be taking a test coming up here, a couple of tests coming up pretty soon, right? You want to look good on the exam, right? You want your work to look like you know what you're doing, right? Keep in mind one thing that graders always do is they're trying to interpret from what you've written, how much do you understand these relevant ideas? So with that in mind, right, it'd be a really good idea on a question like this concerning line integrals in R3, don't talk about divergence. It's got nothing to do with the question. And the diagram, by virtue of it being way over here, right, is telling you divergence doesn't have anything to do with this. And likewise, triple integrals don't have a thing to do with this question. There will be no three-dimensional solids that will be relevant to this question. Right? So make sure, no, that's the wrong word. Your work will look a lot better if you make an effort to avoid, just don't even write any of this stuff that I have crossed out in red, don't even write it down on the page that's asking about a line integral, because it makes it look like you think it might have something to do with a line integral, which makes it look like you don't really understand how to compute line integrals, and it also makes it look like you don't really understand Gauss's divergence theorem. So it's a bad look, if nothing else. Does that make sense? Okay. So that's useful information to know what not to do. Okay, so let's keep that in mind. All right, now, so we have line integral. We were given a vector field. We were given a curve. What does the line integral tell me to do with these things? Well, the line integral is the diagram, the diagram is telling me right here, look at where the vector field is. Diagram is telling me, compute the curl of that vector field, right? This position is the input for that operator, the curl operator. So compute the curl. Even if you don't know why you're computing the curl yet, even if you haven't decided what you're going to do with that information, the fact that you're feeding into this operator and that you're going to compute the curl, if you write that down on the page, it's going to look like, okay, well, at least you know what the right first step is, and what you're going to do with it you'll figure out later. But this is a natural, reasonable first step to take. Does that make sense to everybody? Okay. What does it suggest we should do with our curve? Well, again, just look at which way the arrows point and all. It says here, apparently, my curve that I was given, I should think about the boundary points of that curve. So that's what we're going to be doing first. We're going to take our given vector field, compute the curl. We're going to take our curve and look at the endpoints. And let's see what happens. Then we'll draw conclusions as we can. And by the way, notice that we've established our context. We've established that we're going to compute the appropriate operator and boundary. And now we're going to think about what our consequences are going to be from that. Okay, here we go. I already forgot my color choices. Okay, let's see here. So we're going to compute for this vector field. We're going to compute the curl. All right. Now there's a certain amount of arithmetic. Trivial algebra, I guess we should call it. That goes into computing this curl. And make sure you know the formulas, right? I mean, I hope that's a given. You have to be really polished, quick. You need to be able to crank out curls, crank out divergences quickly and reliably, proficiently, as we would say. And let's see here. So, for example, a y partial of this and then minus the z partial of that, you get 0. And then various other partials to be computed and subtracted, and you go through, and it turns out you get 0. How about that? What does that tell us? We'll go back to the diagram. We've computed the curl. We got 0, and remember, that tells us a bunch of information. In particular, among other things, that tells us there is a function whose gradient is that vector field, or as I would like to say, I think a little bit more glibly, this vector field has an anti-gradient. Everybody on board? Okay, so what? What is that? What's the punchline? What does that have to do with me diagnosing how I'm going to solve this problem? Well, it helps me because that's the critical item that I would need in order to be able to use the fundamental theorem of line integrals. So I now know that not only is the fundamental theorem of line integrals potentially applicable here, it is literally applicable. This will do it. I can use the fundamental theorem of line integrals to answer this question. Now, again, how did I get to that conclusion? I mean, I suppose you could think of this in different ways, but I think it's nice to point out that just by kind of following the instructions kind of implicit in how this diagram is organized is what allowed me to draw that conclusion. The diagram guided me toward this as a candidate method. That's, I think, pretty handy. Okay, all right. Now, next thing, I need to apparently look at the boundary points of this curve. Okay, what is my curve? Alrighty, well, my curve is parametrized already. Not sure if that's going to be useful. By the way, don't forget curves might be parameterized. They might be given as level sets. They might be given as intersections of other things. They might be described verbally. All right? There's a bunch of different ways to describe a curve, so it won't always go down as I'm about to describe. But one way or the other, you need to understand your curve well enough to be able to decide what its boundary is. And this being parameterized, I'm just going to take my starting value of t and plug it in and see what I get. And then I'm going to take my ending value of t and plug it in and see what we get. And I don't remember how this worked out, so let me think this through real quick. My starting point, plugging in t equals 0. 0. E to the power of 0 is 1, and then again with the 1. So that's my starting point. Let's see, my ending point for this curve, plugging in t equals 1. Now I get minus 1, 1, and e squared. All right, is that cool? I know the starting point, I know the ending point. What does that allow me to conclude? Well, pretty easy to notice. These 2 points are different. Right? So this starts and ends at different points, which means, not to scale or anything, but just, strategically is, symbolically, our curve is kind of like this. It starts at one point, it ends at a different point. It does not close up. Therefore, it is not a closed curve. Therefore, there's no way this could possibly be a boundary. I mean, just look at the geometry. You're not going to hold in any sheep if this is what your fence looks like. Right? It doesn't enclose an inside. Does that make sense geometrically? All right, so that's kind of a geometric way to think about it. But again, going back to the diagram, I did not get 0. So there is not a surface whose boundary is that curve. Or again, I think it rolls off the tongue a little more nicely. There is no anti-boundary. Now, what does that tell us? Again, to our goal at the moment of trying to diagnose and figure out what are our options, how many different ways might I be able to solve this, compute this line integral they asked us to compute. Well, there is no anti-boundary surface. So there's no way that I can use Stokes's curl theorem because there is no surface over which to even talk about a flux. So this is a non-starter right here. Stokes's curl theorem is just out of the question. Not going to happen. Is that cool? So we know one possible line of reasoning that will definitely get us to an answer, and we also know one that even though kind of at casual, superficial glance at the start we thought might have been applicable, we know now that Stokes's curl theorem is not going to work. It does not apply. Our curve is not a boundary of anything. And of course, we concluded instantly Gauss's theorem is silly, ridiculous, obvious nonsense. All right, so we're in business. This question, you should use the fundamental theorem of line integrals. And now, I guess one other thing you could do, again, we've already discussed, actually, let me do this. Let me get rid of all of that stuff. We've already discussed how any vector field that is a gradient, aka any vector field whose curl is 0, regularity issues aside, is also path independent. So yeah, I could pick a different curve, and I could, I suppose, look at these starting points and ending points, and I could parameterize maybe the straight line that goes from here to here. I guess you could do that too, but honestly, most of the time, if the fundamental theorem is an option, yeah, usually that's your best option. And so I wouldn't mess with path independence here. I don't think there's enough to be gained. Okay, so I say we have successfully diagnosed this question. This is a fundamental theorem of line integrals question, and I'm going to leave all the details to y'all. We've done that kind of stuff before, but now we know how to do this problem. Okay, let's go to the next one. Okay, now again, we have a computation of a line integral. So let's think about context. Well, we are clearly in 3 dimensions. The vector field and the parameterized curve, both clearly 3-dimensional. So R3 diagram, looking at a line integral. So in fact, our context for this question is the same as our context for the last question. And let me get rid of all this junk here. We have a line integral to compute. Vector field is given. Curve is given. The diagram is telling us to compute the curl. It's telling us to think about the boundary points of our curve. Let's do that. Let's see what we get. Let's draw our resulting conclusions, and then let's decide which of these 2 theorems might be applicable. All the while making very careful not to write down divergence anywhere, real bad look, right? Don't talk about 3-dimensional solids or triple integrals, or don't say Gauss, right? Real bad look. Okay. All right, so here we go. Let's compute the curl. This vector field curl is, you know what? You can compute the various partials and subtract accordingly and put them together, and what you're going to find is curl is 0 here. In fact, you're going to find that's a really easy calculation. Real quick observation, not that this happens a huge amount, but notice that my first coordinate is a function of only x. My second coordinate is a function of only y, third coordinate only z. So when I'm taking various cross partials, I'm always taking derivatives of constants. So this is just a bunch of zeros, and curl is 0. Is that cool? All right, so good news. We got, wrong color, we got 0, which means there is an anti-gradient, which means the fundamental theorem is on the table. That's an option. We could do it that way. All right, let's look at the other side. Let's compute now the boundary of this curve. So again, I'm going to plug in these points and see what we get. And here we go. 0, 1, 1, and then it ends at 0, 1, 1. How about that? This curve starts at a point and ends at exactly the same point. Now that's just arithmetic. That's just plugging in, right? And again, you can think about this geometrically, or you can think about this diagrammatically. If my curve starts at one point, and if it goes around in whatever way, I don't really care, and then ends at the exact same point, then it's a closed curve and a boundary, and so that's a good thing. Diagrammatically, again, boundary being 0 means there is an anti-boundary surface. And that means Stokes' theorem is on the table. Right, I mean, the whole worry, the big question, can I apply Stokes' curl theorem? The concern is not whether will I be able to compute the curl. Yeah, that's not a problem. That's a formula, plug and chug. That you can always compute the curl. The question is there an anti-boundary surface to go here? That's the worry. That's what very likely is not true in general. But since we know we have an anti-boundary surface, I don't even need to know what it is. I know Stokes' curl theorem is an option. Okay, so punchline then. Again, we were asked to compute a vector line integral. Now we have two options. One thing I could do, I could find my anti-gradient function, plug in my two boundary points, which are the same point, and subtract per this formula. Or I could take my curl field and over my brand new, at least the anti-boundary surface that I know exists, even though I haven't identified it yet, I could compute a flux by way of this theorem. So those are your options. Yeah, kind of three options really, because I suppose it always remains you could literally plug and chug this directly by brute force. Right? You can take your curve already parameterized, plug it into your vector field. Don't forget dx is x prime dt. All that business, you just pull back through the parameterization. So you kind of have three options here, and take a pick. Everybody okay? Now I'll point out the first and third options are actually both pretty awesome. As follows. The curve starts and ends at the same point. The anti-gradient, f here, that I will be plugging the start and end points into, whatever that function is, I will be plugging into it the same points. So I am going to be subtracting some value from itself. So pretty clear, pretty immediately clear that this formula right here is going to give me 0. So that'd be a pretty easy way to do it. I think it's hard to argue using the fundamental theorem and f of some point minus f of that same point. Yes, of course it's 0. Yes.
If we say all of that, do we still need to find f?
That's the beautiful thing about it. You don't even have to find the f because it doesn't really matter what it is, because all that matters is you're plugging the same point into the same function. So yeah, right. Okay, here's another bit of good news. This is a pretty great option too. So there's some surface. I don't need to know what the surface is because apparently I'm going to be computing the flux through that unknown surface of the vector field that is 0. And it doesn't really matter what that surface is. If the vector field is 0, then the flux is also 0. So this question actually has 2 pretty fantastic methods of solution. That's pretty handy how that works out sometimes. Yes?
Can there be a case where like one of them is like 0 and the other isn't? Like the point's a 0 and the vector field isn't?
Oh no. Well, so that would be. So you're saying that like where this would be 0 and this would be not 0?
Yeah.
No, that's not possible because they're computing. They're literally computing the same thing.
Right.
So yeah. So if you ever good general rule of thumb, if you ever have something you want to compute and if you compute it 2 different ways and if you get 2 different answers, something went wrong. Yeah, exactly. Yeah. So that's why I say take your pick of these solutions. Once you've done one, you know what the other has to give you. Yeah.
For the fundamental theorem of line integrals, if you wanted to compute f, how would you?
Oh yeah. So that's we have a. I'm just going to do a hand wave back to the end of section 6.2. I can't remember. But anyway, in the section where we talked about the fundamental theorem, 6.3. I'm pretty sure it's 6.3. Yeah, there's a that's the one with the game, where you take the x antipartial of p and the y antipartial of q, and then you have these partial constants that can be kind of almost anything, and then you play the game and you try to get it to work out. Yeah. Okay. So good options there. And again, thank you, Diagram, for helping to guide us to what our options are. Right. So it tells you to compute the curl of your integrand, to take the boundary of your given curve, and to what to conclude, and therefore which theorem applies as a result. The way the diagram is laid out does that automatically kind of for you, again, if you interpret correctly. Okay. All right. Okay. Okay, moving along. Let's look at example 3 here. Again with the line integral, again in 3 dimensions. So same context. So let's follow the same rules as the diagram would suggest. Our vector field, we're going to compute its curl. Our curve, we're going to look at the boundary points. Let's just see what happens. Okay, so vector field, we'll compute the curl, and this one I happen to recall from my earlier lecture is -1, -1, -1. And make sure to check me on that, both because I am fallible and also because you want to make sure that you're proficient with how to compute these things. So what does that mean? Well, it's not 0, and being as it is not 0, let's see, back over to here, I got not 0. That means there is not an anti-gradient. That means the fundamental theorem at line integrals is not applicable. Don't even look at this theorem for this question. It does not apply. Is that cool? Okay, looking at the boundary points now. Let's see here. So, okay, now this is a little bit weird. This curve is given to us as an intersection of two other curves, and then a vague statement about the orientation. We'll cross that bridge if and when we get to it. But let's draw a picture of our curve here. I'm going to draw an axis system like this. We have this cylinder here. Like that, and then we have, let's see, this plane there. These are always hard to draw. Like that. And now I appeal to your sense of geometry. You got to think about, how does this orange plane, how does that intersect with this purple cylinder? And that intersection is our curve. That intersection then is, oh gosh, I mean, it's something vaguely kind of like this. It's a sort of a tilted ellipse. Is that cool? A tilted ellipse. Now again, I just got to make a geometric appeal, right? There's no algebra to be done to conclude the following, but it's a closed curve, which it is. Right? The picture says so. And being a closed curve, that means the boundary points. Well, there are no boundary points. So I'm going to say you get 0. And arguably, there's a way of viewing it then that means that, yes, there is a surface whose boundary is that curve. In fact, I can tell you what that surface is, the anti-boundary surface. You can, again, see right here in the picture. Let's see here. I guess I will use the dark blue here. There's my anti-boundary surface. How are we doing? Everybody good so far? That was the big worry. I mean, to the question of, can I use Stokes's curl theorem? Well, apparently yes, I can use Stokes's curl theorem because my original line integral, I computed the curl. It wasn't 0, not that matters, but anyway, the point is I computed the curl. I have an anti-boundary surface. I have everything I need to work with this thing on the right. Again, we have the, why don't I color code this better? I have an anti-boundary surface. That's the surface over which I'll be computing the flux of the curl. And that's an option. And off you go. What do you think? Okay. So here's the thing. I've made this observation before, and I'm sure I'll make it again. Again, we were asked to do this computation. We have now found that we could instead do this calculation. I think you should always, take a step back and ask yourself, well, yeah, but I mean, is this helping me? Would I actually rather compute the flux? Or might I just rather compute the line integral? I mean, I could plug and chug the line integral. Apparently, I'm going to have to plug and chug this flux integral. So, which would I rather plug and chug? And, there is no consistent sort of like always the one or never the other. It depends on the geometry of the situation. It depends on the algebra. So, do take a nice look at each of your options and think it through. So, for example, let's think about if I look at the curl field and the anti-boundary surface, how would I compute a flux? Well, going back to the thing here, here's my anti-boundary surface. Probably going to be parameterizing that thing. Do we know how to parameterize this surface? Well, conveniently, this surface that I'm looking at, now again, geometric appeal, right? But that surface sits inside of this plane. Yeah? That plane has this equation in which I can pretty easily solve for z. So I can graph parameterize that new surface. That's not that bad. right? The only thing I'm a little concerned about is the domain for that graph parameterization. The domain will be the unit disk in the xy plane, which means I'm going to have a round domain, which means I'm probably going to end up using polar coordinates. Again, doable, but it's not going to be a freebie. Okay, that in mind, now let's look at our other option. Our other option, reminder from the diagram, other option is to just compute the question as it was originally phrased. Original curve, original vector field, just compute the line integral. So how would I do that? Notice that my original curve was not parametrized. So if I want to brute force this question, right? Pull back through the parameterization, I'm going to have to parameterize the curve. Not that bad in this case either. X and y become sine and cosine. Z is just negative x minus y. Not that hard to write down the parameterization. The vector field, not that bad. You pretty quickly would turn this line integral into just some single variable trig integrals. And again, not exactly freebies, but not exactly the scariest thing you've ever seen either. So honestly, I think both of these approaches would be worth cranking out. Good exercise for you all to do, right? But crank out both of them to see which one you like better. And as I recall, I think they're about the same. I don't really have a strong preference between them. Yes?
So when we parameterize the curve, are we just parameterizing like x plus y plus z equals 0?
No. So parameterizing the curve, see the curve is the set of points that satisfy both of these equations, right? So if you just look only at this one equation by itself, that is a plane. And parameterizing a plane is a different thing, right? I mean, we're interested not in the plane at this point. We're interested in the curve itself. And the way that you get this curve from this plane is by noting that this cylinder is what, sort of cuts off the curve inside the plane. Does that make sense? Yeah. Okay. All right. So that's that option. Okay. Next one. Very similar looking question. Same vector field. Therefore, the same curl. Oh, yeah, question. I'm sorry.
How do you know, it feels like sometimes you need to use the stretching factor and sometimes it's like already included. I guess how do you know what you need to use or what isn't?
So the stretching factor is something you do that you put in when you're doing a pullback, right? And so if you're making if I were going to make a geometric argument about the direction that the tangent vector points and stuff like that, there's no stretching factor because I'm not doing a pullback, right? On the other hand, if I were to rewrite this by way of its parameterization, I am literally pulling back through the parameterization, right? And in that case, there is a stretching factor. Now, there's a bunch of different formulas. I recognize there's a bunch of formulas you just have to know. When you pull back a vector line integral through a parameterization, the stretching factor is built into the x prime. The stretching factor is the magnitude of x prime, right? But it's already built into the x prime that's in there. And so there's nothing additional to add. There is no stretching factor to add. You've already added the stretching factor when you wrote down x prime. Does that make sense?
So you're just dotting it through it.
Yeah. That's right. Yeah. You just have to know the formulas applicable to whatever kind of integral you're talking about. Yeah. Right. Okay. So again, same vector field. That means the curl is the same. We still have curl is -1, -1, -1. Now this curve here is different, not super different. It is, after all, the same cylinder. And what's different is we're intersecting with a different plane. This plane x minus z. So, I mean, it's a different plane, but, I mean, structurally it's not that different. It's still a plane intersecting a cylinder. We're still going to have an ellipse. Let me draw that on here. So here's our curve. We're going to have pretty much the same story breakdown because, again, so much is similar. We already computed the curl. It wasn't 0. There is no anti-gradient. Forget about the fundamental theorem of line integrals, not on the table. Our curve is still an ellipse. It still has no boundary. There still is an anti-boundary surface, and we still can use Stokes' curl theorem. So all of this still applies. Same two choices. Do I want to parameterize the curve and brute force it? Or do I want to cite Stokes' theorem, parameterize the surface instead? Or maybe play other games with one of these flux intervals instead. Okay, so there is something importantly different about this question. This is subtle. I remind you that you should always be on the lookout for good fortune. Always just, head on a swivel looking for, hey, how might I be getting lucky here? Right? So what I'm going to do is I'm going to write down what this integral turns into using Stokes' theorem, and then we'll talk about how awesome it is. And here we go. Let's see here. This integral right here, right, by Stokes' theorem, it would be flux through this new surface of, let's see, our curl let's see here, dot. Now, dot our normal vector ds. Or, some people, myself included, like to write this as a ds vector, but here I'm going to write it as little n times ds scalar. And I claim that we are one clever observation away from being done with this question. No nasty cranking it out, no parameterizing. There is a beautiful little observation to make here. And here it is. Let's think about our surface here. Our surface, well, it's entirely contained in this plane. This plane has a really easy equation. That really easy equation, which I'm going to rewrite as follows, x, that's 1x plus 0y plus negative 1z equals 0. And notice I can read the normal vector right off of that plane. Now, if I were to claim this normal vector as 1, 0, negative 1, well, it isn't really. That's, first of all, it has to be normalized. It has to be a unit vector. Second of all, there's the orientation question. I don't actually know if it's oriented like this or like that. I'd have to think about the orientation on the curve and infer from the right hand, the thumb swirl whole business about the surface. But that's just going to be a plus or a minus. And what I can write down kind of for free is that the normal vector here, just for artistic convenience, I'm going to draw it downward. I don't know. But that normal vector is plus or minus unknown orientations I haven't messed with yet. 1, 0, negative 1 from the geometry of that plane, and then normalizing by dividing by the square root of 2. So the normal vector here is like that. And game over, right? Because this curl dot that normal vector is obviously 0, and we put our pen down and walk away. Everybody see that? Now, this is just one of these things you get lucky, right? It just happened to be that this right here, right? This was the giveaway, right? That's telling you about your normal vector. And yes, there's questions that remain that under different circumstances we'd have to think through. But done. So always be on the lookout for good news like this. Now, the previous one that we did, that was very, 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 very similar, right? No such luck. Here, the normal vector is 1, 1, 1. The curl dot that normal vector, that's not 0. The orientation would therefore matter, whether it was a plus or a minus. I'd have to think through the orientation. I'd really have to parameterize the surface, if only to figure out what the stretching factor is. I'd need that capital N, in other words. So on this question, no freebies. But on this practically identically phrased question, nice little freebie. Okay, we'll call it a day right there. Y'all have a great weekend. See you on Monday.